Hey everyone, and welcome. Today we're tackling a fun grid problem from LeetCode. It involves 3 children collecting fruits in a dungeon, and our job is to figure out the maximum total they can get. It seems complicated at first, but we'll break it down into simple, manageable pieces. Let's get started. So here's the official problem description. We're given a square grid of fruits. The main thing to understand is that 3 children start at 3 different corners and move through the grid. We need to find the maximum total fruits they can possibly collect. The key rule is that if they land on the same spot, only one of them gets the fruit. Let's visualize the paths. We have one child starting at the top left corner, aiming for the bottom right. Another starts at the top right and heads to the bottom left. And the third starts at the bottom left, moving towards the top right. They all take a fixed number of steps to reach their destinations. Now here's the first major insight that simplifies everything. Let's think about the child starting at the top left. To get from row 0 to the last row in exactly that many steps, they must move down by 1 row every single time. The same logic applies to columns. They must move right 1 column every time. This means their path is totally predictable. They will always travel along the main diagonal of the grid. Because we know exactly where that first child goes, our strategy becomes much clearer. First, we just add up all the fruits on that diagonal path and put that sum aside. Then, we can imagine those rooms are now empty. This leaves us with the other 2 children. The best way to make sure they don't step on each other's toes and get the most fruit is to have them operate in separate zones. We'll have one collect fruits only from the top right half of the grid and the other from the bottom left half. Let's use the example from the problem. First, we handle the diagonal path. That's 1 plus 6 plus 11 plus 16, which gives us 34 fruits. Now we treat those spots as empty, as you can see in the updated grid. Our next job is to find the best paths for the other 2 children in the remaining parts of the grid. This type of problem, where we need to find an optimal path by making a sequence of choices, is a perfect candidate for an approach called dynamic programming. We'll build a sort of cheat sheet, or a DP table, where each cell will tell us the maximum number of fruits we could have collected to arrive at that exact spot. The core logic for our dynamic programming is pretty simple. To figure out the best score for any given room, we take the number of fruits in it, and we add that to the best score we could have had in the row right above it. We look at the 3 rooms we could have come from, the one to the top left, the one directly above, and the one to the top right, and we just pick the one that had the highest score. Okay, here's the overall structure of the solution in Python. It's a bit long, so we've split it up. This main function orchestrates our whole strategy. First, it calculates the diagonal sum. Second, it creates a new grid where the diagonal fruits are set to 0. Third, it calls a helper function to find the best path in the upper triangle. Fourth, it does a cool trick by transposing or flipping the grid and calling the same helper to find the best path in what was originally the lower triangle. Finally, it adds all 3 results together. Now let's look at that helper function. Its job is to find the single best path score within the upper triangle of whatever grid it's given. It creates a DP table full of zeros. Then, it iterates through the grid, but notice it skips any cell that isn't in the strict upper right triangle. For each valid cell, it applies our recurrence logic. It finds the max score from the 3 potential cells in the previous row, adds the current cell's fruit, and stores it. The final result is just the largest number that ends up anywhere in our DP table. So, how efficient is this? The time it takes is on the order of n squared, where n is the size of the grid. This makes sense, because our dynamic programming approach has to visit most of the cells in the grid. For space, a simple implementation would also use n squared space for the DP table. But, as the official solution notes, you can be clever. Since you only ever need the results from the previous row to calculate the current one, you can optimize this down to order n space. So to wrap up, what are the big ideas here? First, always look for a way to simplify the problem. For us, that was realizing one of the paths was fixed. Second, breaking a problem into smaller independent pieces is a fantastic strategy. We solved for 2 separate triangles instead of one big mess. Third, remember that dynamic programming is your go-to technique for these kinds of optimal path problems. And finally, when you see symmetry, think about clever ways to reuse your code, like we did by flipping the grid. And that's it for this one. I hope this breakdown was helpful. If you found it useful, please hit that like button, and maybe subscribe for more explanations like this. If you have any questions or a different way to solve it, drop a comment below. I'd love to hear it. Thanks for watching. Keep up the great work, and I'll see you in the next one.